Hello, today we're going to go over the mean value theorem. Mean value theorem is one of the most important theorems in single variable calculus. So first of all, what is the mean value theorem, and then how do we prove it? Okay, so the mean value theorem, this would be like basically the last theorem and the main theorem we'll prove today. Mean value theorem tells you if you have a function from between 2 points A and B, under some certain assumptions, some certain conditions, if you look at the slope of this function, the average rate of change, there is some point in between A and B that the slope at this point is the same. So slope at that point is f prime of c is the same as the average rate of change. Rate of change is rise over average rate of change is rise over run. So this is the mean value theorem under some certain conditions. In order to prove the mean value theorem, we need some preparation. The first thing we need is the definition of local maximizer and local minimizer. We say a function has a local minimum at a point when the value of the function at that point is smaller than or equal to all of the values close to that. Now, how do we articulate that? This is the definition that can articulate this this concept. So a number x naught in the domain of a function f from d to r is said to be a local minimizer if there is a neighborhood I of x naught for which f of x naught is less than or equal to f of x for all x inside I intersection with d. So I is a neighborhood, meaning that it's an open interval containing x naught. So if you want to look at an example, I'm going to draw an example here. If you look at this function has a local minimum here because there is some interval around it that the value of the function at that point is the smallest over this interval. However small that interval is, that's okay as long as it is an open interval containing that point. So that's called a local minimizer. And we say a point x naught is a local maximizer if the exact same thing happens except that f of x naught is greater than or equal to f of x for every x inside I intersection with d instead of less than or equal to. We say x naught is a local extreme point if it is either a local maximizer or a local minimizer. Okay, so one thing about local minimizer and local maximizer is that the derivative would have to be 0. If you look at the local maximizer, which is right here, you can clearly see that the derivative is 0 at that point, or the slope is 0. And the main thing that I need about that is the fact that the function is in fact differentiable at that point. Okay, so let's state and prove the next theorem. Suppose I is a neighborhood of a real number x naught, and x naught is a local extreme point of f. F from I to r. So x naught is a local extreme point of f from I to r. So we have a local extreme point, and we want to show that if f is differentiable at that point x naught, then f prime of x naught is equal to 0. So there is a local extreme point, meaning that it's either a local minimum or a local maximum. Let me just assume that f is has a local minimum at x naught, or x naught is a local minimizer. So assume, and then for local maximizer, the idea would be, the proof would be nearly identical. You just have to flip some of the inequalities. So assume x naught is a local minimizer for f. Thus, there is a neighborhood some neighborhood of x naught, let's say a comma b, or you can even make it symmetric. Yeah, let's just say a comma b of x naught such that f of x naught is less than or equal to f of x for all x inside that neighborhood. Okay, we will go ahead and prove that f prime of x naught is in fact 0. So let's look at f prime of x naught. F prime of x naught is the limit as x approaches x naught of f of x minus f of x naught over x minus x naught. Now, take a sequence of numbers that approach x naught. Since x naught is in this interval, we can take a sequence that approaches x naught from the left, and we can also take a sequence that approaches x naught from the right. So let xn be a sequence in AB such that xn is greater than x naught and xn approaches x naught. For example, you can take xn to be x naught plus b minus x naught over n. So if you take this sequence, as n approaches infinity, this approaches x naught, and it is in the, so I'm going to take that and put it 2n. This is less than or equal to, this is clearly greater than or equal to x naught, and it's less than or equal to b, less than b. So if you take this sequence, and just to give you an idea of how I came up with this sequence, take this interval from a to b and look at the point x naught, take this and divide this one in smaller pieces, so 2 and then 4 and then 6 and so on. And when you do that, you get to a sequence that approaches x naught from above. Now, since f of xn is greater than or equal to f of x naught, f of xn minus f of x naught over xn minus x naught is going to be greater than or equal to 0. By definition of limit, f prime of x naught is equal to the limit as n approaches infinity of f of xn minus f of x naught over xn minus x naught. However, this fraction is greater than or equal to 0. So that means f prime of x naught is greater than or equal to 0. Now, similarly, let yn inside AB be a sequence with yn approaching x naught and yn being less than y naught. X naught. For example, you can take yn to be x naught minus x naught minus a over 2n. This is clearly less than x naught because x naught is more than a, and it also is more than a because this is less than x naught minus a. Okay, so if we take that, then f of y naught is greater than or equal to f of x naught because x naught is a local minimum, and yn minus x naught is less than 0. So that means if I look at the fraction, this is less than or equal to 0. Therefore, its limit is also less than or equal to 0. So f prime of x naught, which is the limit of f of yn minus f of x naught, over yn minus x naught is less than or equal to 0. So f prime of x naught is less than or equal to 0 and more than or equal to 0. We obtain that it must be equal to 0. So I'm going to call this one star, and I'm going to call this one double star. So combining these, we obtain that the derivative of f at x naught must be 0. So if you have a local minimum, the derivative must be 0 at that point, assuming that the function is differentiable. Okay, so now let's see one of the main applications of this theorem that we just proved. And this is something you called in single variable calculus, you called a critical point, a point that derivative of the function at that point is 0. Okay, so next we're going to talk about the Rolle's theorem, which is a specific case of the mean value theorem. So Rolle's theorem tells us this: if you take a function that the values at the endpoints are the same, so there are some certain conditions that are needed. We need our function to be continuous over the closed interval and differentiable over the open interval. If the values at the endpoints are the same, then there's going to be at least one bump here, which means there's going to be some maximum or minimum at some point, and at that point the function has a derivative of 0. Okay, so suppose x naught. Okay, first of all, let me specify this first. Since this function is a continuous function, there would be a maximum value. So by the extreme value theorem, we showed that every continuous function over a closed and bounded interval attains its maximum and minimum value. By the extreme value theorem, f attains its maximum and minimum values on AB. Assume that x1 is a maximizer and x2 is a minimizer for f from AB to R. Okay, if this point x1 is inside the open interval, if x1 is inside open interval, then x1 is also a local maximizer. Local maximizer cannot be endpoints because it has to be an open interval. So if you go back at what we did here, I is a neighborhood. In order for it to be for the derivative to be 0, I need I to be a neighborhood. So here I do have a neighborhood because I assume that x1 is inside the open interval. Then x1 is a local maximizer, and by theorem, the previous theorem 5.6, its derivative must be 0. And that's exactly what we wanted to prove. We wanted to prove that derivative of this function is in fact 0 at some point. Okay. We showed that there is some c between a and b, that f prime of c is 0. Okay, so now, but if that's not the case, it means x1 must be an endpoint. Similarly, if x2 is in the interval, open interval, then f prime of x2 is 0. Now, assume neither of these two happens. Assume neither x1 is in AB nor x2 is in AB. So it means the maximum and minimum happens at the endpoints. Thus, x1 and x2 are both endpoints. Note that the endpoints have the same value. F of A and f of B are the same. Thus, the maximum and minimum values of f are the same. That tells us that this function is a constant. Thus, f is a constant. So f is a constant function, and we know derivatives of constants are 0 by the power rule, I guess. Thus, f prime of c is 0 for every c inside the open interval. And this finishes up the proof. Okay, next we're going to do an example. Prove that the equation x cubed plus 3x plus 1 equals 0 has a unique solution. So first we're going to have to show there is a root for this equation. Then we're going to have to show that there's not more than one root. So in order to show the existence of a root, we often use the intermediate value theorem. So let f of x be x cubed plus 3x plus 1. Note that f is continuous. I need continuity in order to be able to use the intermediate value theorem, because it's a polynomial. F of 0 is 1 and f of negative 1 is negative 3. Since 0 is between negative 3 and 1, by the intermediate value theorem, there is some x between negative 1 and 0 such that f of x is 0. So there is a solution to the equation. Now we will have to show that there are not more than one solution. So on the contrary, assume there are two solutions. F of A is equal to f of B is equal to 0 for some A less than B. By the Rolle's theorem, the theorem that we just proved, there's got to be some C between A and B such that f prime of C is 0. But watch what happens if you take the derivative of that. So that tells us 3c squared plus 3 must be 0, which means c squared must be negative 1. But that's negative. This violates the c squared equals negative 1, violates the trivial inequality. Okay, and that contradiction shows the uniqueness. Okay, finally we will prove the mean value theorem. Okay, so I stated the mean value theorem before, but the more I guess, rigorous statement is that you need the function to be continuous over the closed interval. You need it to be differentiable over the open interval. Then there is a C, that the rate of change, instantaneous rate of change of the function at C, is the same as the average rate of change of the function over the entire interval. Notice that f of b minus f of a over b minus a is the same as f of a minus f of b over a minus b. So it doesn't matter whether you, which one comes first. It could be a comes first or b comes first. Just be careful that you are not swapping them only in the numerator or only in the denominator. Okay, so now if you again, I'm going to go over the idea of the proof on the right, and then we'll write down the solution on the left. So we would like to prove this equality. Okay, so if you look at the Rolle's theorem allowed us to show that f prime is equal to 0 under some certain conditions. So here I'm going to bring everything to the same side. So I have f prime of c minus a constant. So the question is, can I write down this constant as derivative of something? And the answer is, if you put an x in front of it. So look at this function, f of x minus f of b minus f of a over b minus a times x. If you differentiate this function, you get the top one. So in order to be able to use Rolle's theorem, we need to show this function satisfies the two conditions. Or I guess the three conditions. Let g of x, g from ab to r, be given by g of x equals f of x minus f of b minus f of a over b minus a times x. Since f and x are continuous on AB and differentiable on the open interval AB, so is the function g. So function g is continuous over the closed interval and differentiable over the open interval. Now let's evaluate g of a. G of a, if I show that g has the same value at the endpoints, then I can apply Rolle's theorem. G of a is f of a minus f of b minus f of a over b minus a times a. So let's take the common denominator here. We get b minus a times f of a minus a f of b plus a f of a. And the a f of a cancels. So that means g of a is equal to b f of a minus a f of b. The a f of a cancels, divided by b minus a. Let's plug in b. Hopefully we get the same thing, and if in that case we will be able to use the Rolle's theorem over b minus a times b, multiplying by b minus a, taking the common denominator, bf of b plus bf of a over b minus a. bf of b cancels, we get minus af of b plus bf of a over b minus a. And if you compare the two, both of them are bf of a minus af of b divided by b minus a. Therefore, g of a is equal to g of b. So by the Rolle's theorem, there is some c between a and b such that g prime of c is equal to 0. but g prime is just f prime minus that constant, minus this. So it becomes f prime of c minus f of b minus f of a over b minus a equals 0, which means f prime of c is equal to f of b minus f of a divided by b minus a. And that's exactly what we wanted to prove. So this brings me to the end of this video. So what we did today was we proved the mean value theorem, and along the way we showed that if you have a local minimum for a function at a point, then the derivative, or a local maximum, then the derivative would have to be 0. Okay. So this brings me to the end of this video. If you would like to continue with this class, feel free to subscribe, and I will see you in the next video.